Did you know that the internet, the very fabric of our digital lives, was born from the minds and machines at CERN? But that's just a taste, a mere appetizer to the cosmic feast this place offers. CERN is home to the world's largest machine, a colossal marvel of engineering capable of recreating conditions that existed fractions of a second after the Big Bang itself. Imagine a window into the very dawn of existence. Now, why would we dare to tamper with such primordial forces? Because within those fleeting moments, within the fiery crucible of the nascent universe, lie the answers to questions that have haunted humankind since we first gazed upon the starlit sky. Why does anything exist at all? What are the fundamental building blocks of reality? What is the destiny of the universe itself? Could this machine, this modern-day oracle of science, help us uncover extra dimensions hidden from our perception? Could it shed light on the enigmatic nature of dark matter, the invisible hand that shapes the cosmic web? Could it even reveal new laws of physics, rewriting the very textbooks of scientific understanding? Let us embark on a journey, a voyage of discovery into the heart of CERN, and explore the profound mysteries it seeks to unravel. We humans, we've come a long way. From our humble beginnings on the savannas of Africa, to building cities that touch the clouds, to venturing into the vacuum of space. Yet for all our progress, some questions remain eternally vexing, echoing through the corridors of time. Why is there something rather than nothing? Why does the universe exist at all? It's a question so fundamental, so disarmingly simple that it's easy to brush aside. But ponder it for a moment and you'll feel the weight of its profundity. We've peered into the cosmic abyss, mapped the galaxies, and yet 95% of the universe remains shrouded in darkness, a cosmic enigma we call dark matter and dark energy. Nestled on the border of Switzerland and France, beneath the majestic shadow of the Jura Mountains, lies a monument to human curiosity and ingenuity. CERN, the European Organization for Nuclear Research. This isn't just another laboratory, it's a global endeavor, a testament to the power of international collaboration, uniting minds from over 100 countries in a shared quest to unravel the universe's deepest secrets. Within CERN's sprawling complex, physicists, engineers, and technicians from all corners of the globe work tirelessly, pushing the boundaries of knowledge. Their tools? Some of the most sophisticated and powerful machines ever built, capable of peering into the very heart of matter, recreating conditions that existed fractions of a second after the Big Bang. CERN's story isn't just about groundbreaking science, it's a testament to the power of human collaboration. Founded in 1954, in the aftermath of a devastating world war, CERN emerged as a symbol of unity and scientific cooperation. It was a bold vision, to create a neutral ground where scientists from nations once locked in conflict could come together, united by a shared passion for understanding the universe. From its inception, CERN has been at the forefront of particle physics, pushing the boundaries of knowledge with each passing decade. Imagine a machine of such colossal scale, such mind-boggling complexity, that it stretches the very limits of human engineering. Now bury it hundreds of meters beneath the Earth, threading its way through the Swiss-French countryside in a 27-kilometer ring of superconducting magnets, cutting-edge detectors, and enough cabling to circle the Earth 6 times over. This, my friends, is the Large Hadron Collider, the LHC, the most powerful particle accelerator ever built. Protons, those tiny particles residing at the heart of every atom, are accelerated to nearly the speed of light, whipped around the LHC's ring by powerful magnetic fields, their energy levels boosted with each lap until, finally, they collide. For decades, the Higgs boson was the most sought-after particle in physics, a phantom of the subatomic world, its existence predicted by theory but never observed. It was the missing piece in the standard model of particle physics, the framework that describes the fundamental forces and particles that make up our universe. The Higgs boson, you see, was the key to understanding why particles have mass, why some particles are heavy like the top quark, while others, like the photon, have no mass at all. Then, in 2012, after years of searching, after sifting through mountains of data, physicists at CERN announced the discovery of a new particle, a particle that fit the theoretical description of the Higgs boson. Imagine a state of matter so extreme, so unimaginably hot and dense that it existed for only a fleeting moment after the Big Bang. a state where protons and neutrons, the very building blocks of atomic nuclei, melt away, dissolving into a swirling soup of their constituent particles, quarks and gluons. This, my friends, is the quark-gluon plasma, a primordial soup that last existed naturally some 13.8 billion years ago. By smashing heavy ions like lead and gold at incredible speeds, physicists at CERN are able to momentarily recreate the conditions that existed in the universe's earliest moments. For a fleeting fraction of a second, a tiny fireball of quark-gluon plasma blossoms into existence, its properties measured and analyzed by sophisticated detectors. Our universe, for all its grandeur and complexity, is governed by a fundamental principle. For every particle there exists an antiparticle. An electron has its positron, a proton its antiproton, and so on. Now, according to our best theories, the Big Bang should have created equal amounts of matter and antimatter. But here's the rub. When matter and antimatter meet, they annihilate each other in a burst of pure energy. So, if the early universe truly contained equal amounts of matter and antimatter, it should have been a very short-lived affair, ending in a blaze of annihilation before it even began. Yet, here we are, surrounded by a universe teeming with matter, with nary an antimatter particle in sight. We often take pride in our scientific understanding of the cosmos, in our ability to map galaxies and trace the evolution of the universe back to its earliest moments. But what if I told you that everything we see, all the stars, planets, and galaxies, make up a paltry 5% of the universe's total mass and energy? The remaining 95%? It's shrouded in darkness, a cosmic mystery we call dark matter and dark energy. Dark matter, as its name suggests, doesn't emit, reflect, or absorb light, making it invisible to our telescopes. Yet we know it's out there, its gravitational influence holding galaxies together, preventing them from flying apart. Dark energy, on the other hand, is even more enigmatic. We experience the world in 3 dimensions: length, width, height. It's intuitive, it's familiar, it's just how things are. But what if our perception of reality is merely a sliver, a thin membrane, in a grander, higher dimensional reality? What if there are extra dimensions curled up, hidden from our view, yet influencing the very fabric of our universe? This isn't just science fiction, my friends. It's a concept explored by string theory, one of the most promising frameworks for unifying quantum mechanics and general relativity, the 2 pillars of modern physics. String theory suggests that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings of energy. The standard model of particle physics is a triumph of human ingenuity, a testament to our ability to unravel the universe's deepest secrets. It's a remarkably successful theory, explaining the behavior of all known particles and forces except for gravity. Yes, gravity, the force that holds us to the Earth, that dictates the motion of planets and stars, remains stubbornly outside the standard model's grasp. The standard model also fails to explain the existence of dark matter and dark energy, those shadowy entities that dominate the universe's mass and energy budget. Clearly, there's more to the story, a deeper, more fundamental theory waiting to be discovered, a theory that goes beyond the standard model. At CERN, physicists are exploring a plethora of theories that extend the standard model, searching for clues to a new physics. As we've seen, CERN is a place of wonder, a testament to the power of human curiosity and collaboration. It's a place where the universe's deepest secrets are probed, where the boundaries of knowledge are pushed, and where the very nature of reality is questioned. CERN has already revolutionized our understanding of the universe, but the most exciting discoveries may still lie ahead. Could the next particle collision at the Large Hadron Collider rewrite the textbooks of physics? Will we uncover extra dimensions, finally shedding light on the universe's hidden structure? Will we crack the code of dark matter and dark energy, unraveling the destiny of the universe itself? The possibilities are as vast and mysterious as the cosmos itself.